So in this video we're going to start talking about compactness. Okay, so we're going to let X be a topological space. So we're going to talk about open covers of X. An open cover of X is a family, say UI, for I in some index set capital I, of open sets. So each UI is supposed to be an open subset of X. And it has to cover X, i.e. For all X in X, there exists some index I with little x lying in the set UI. So that's what we mean by an open covering. And then a finite subcovering so that means a subfamily. Let's say uj for j and j. So here j is a finite subset I, so we're just using sort of finitely many of the open sets that we had previously. So this has to be j is a finite subset, and this subfamily still covers right, so again, for each point x in your space, there exists j in just one of these finitely many indices, in capital J, with x lying in uj. That's what we mean by an open cover and a finite subcover. And X is compact, we say, if every open cover has a finite subcover. Okay, so obviously it's not obvious from the definition. You've got an open cover of a space. It's not obvious that it has a finite subcover. It's easy to find non-compact spaces where you've got open covers that don't have a finite subcover, but we say it's compact if every open cover has a finite subcover. Okay, so let's have some examples of this. X could be the real line. UN can be the open interval from n-1 to n+1, so that's an open set. So we look at all these sets UN for integers n, and they're going to cover the whole of the real line. We just draw the picture here. So here's the real line: 0, 1, 2, 3, and then U0 is here, U1 is here, U2 is here, etc. Okay, and it's easy to see that these open intervals, they cover the whole line, but but if you just take finitely many of these, then obviously it's not going to contain the whole real line. For example, if you want to be completely specific about it, you look at the maximum of these integers nr and add 3, then that's not going to be in this union. Okay? So the real line, that's not a compact space. Okay, so another example. Okay, so in this case, line across here. So this is a new example. We've got y as the open unit interval, and Vn is kind of almost like the open unit interval, but it stops a bit short. And then, so then if you look at the family of all these Vn's, so that covers the whole unit interval, whole open unit interval there. But if I only use finitely many of these, say Vn1 union up to Vnr, well, you know, these are nested inside each other, right? So as n increases, the set just stretches out a bit more. So this is just the same thing as V max n1 up to nr. And that's never going to be equal to the whole thing. Okay, so if we only use finitely many of the V's, then we don't cover the whole unit interval. So there's no finite subcover. The open unit interval is not a compact space. Okay, so what about spaces that are compact? Well, let's first do a kind of really easy example. So let's consider a finite space. Okay, so we want to prove that that's compact. So remember how does the proof of compactness always has to start like this? We have to say let UI be an open cover. Okay, and then somehow we have to produce a subset J, and then check that the UJs for J and J still cover the space. Okay, so so let's say for I is 1 up to n. Okay, let's call this something different. Let's call this t. For t is 1 up to n, we're going to choose some it in the index set I, such that xt lies in uit. And that's possible because this original family covers x. We're given that it covers x, so every point in the space lies in one of these things. And now it's clear that x can be written as the union of ui1 union up to uin. So we've got a finite subcover. Okay. So finite spaces are compact. Another major source of compact spaces is the theorem for the metric space course, which we need to recall. So firstly, let's say set X in Euclidean space Rn. We're going to say that's bounded if there's a constant, a capital R, such that the norm of every element of the set every element of the set has norm less than or equal to R. Okay, and then the theorem says that X is compact under the subspace topology, of course. If and only if it is both bounded and closed. Okay, so I'm not going to give the proof of that here, because it is there's a proof in the metric space course, or just about any book on metric spaces that you might look at. Okay, so so let's have some examples of that. So remember, Bn is the set of X in Rn with the norm of X less than or equal to 1. Sn minus 1, that's the set of X in Rn with norm of X equal to 1. Okay, so those are both bounded and closed. Delta n, that's the set of X in R, the n plus 1, with xi greater than or equal to 0 for all I. And the sum of the xi's is equal to 1. So of course this implies that each of the xi's individually is less than or equal to 1, and that shows that it's bounded. And then you could look at like the cube, 0, 1 to the n. So all these are compact. Another thing to say, and of course these are all metric spaces, and therefore they're Hausdorff. Remember, every metric space is Hausdorff. So these are compact Hausdorff spaces, and actually, compact Hausdorff spaces, they're very nice class of spaces, just about the most well-behaved class that you might think about. And then we've mentioned before, there's a bunch of interesting examples of all sorts of different phenomena in topology, which we can get from considering spaces of matrices. So let's talk about compactness in that context. Okay, so let's recall we've considered several times the orthogonal group On. That's a set of n by n matrices, n by n real matrices, with the property that A transpose A is equal to the identity. Okay, so we can define f from MNR to MNR just by f of A, say, is equal to A transpose A minus the identity, say. And this is continuous. Entries in f of A are just polynomials in the entries of A, so standard argument shows that that's continuous. And On is f inverse of 0. Okay, I mean the set containing 0, that's a closed set. Preimage of a closed set under a continuous map is closed, so On is closed. Remember that in the matrix space, the distance from A to B is the square root of the trace of A minus B transpose A minus B. So we mentioned this story before. I mean, this is just the we identify the space of matrices with r to the n squared in the obvious way. A matrix is just n squared numbers written in a table. You could just write them out in a row and then they'd be a vector. So MNR is basically r to the n squared. And we explained before that one way to think about just the ordinary Euclidean norm, it turns out to be the same as this kind of thing here. You take the trace of the A transpose A, and that's your norm. Okay, so that means that this is like I say the norm of A minus B. And so the distance from A to 0, or the norm of A, is the square root of the trace of A transpose A. So if A happens to be an ON, then the norm of A is the square root of the trace of the identity. But the trace of the identity is just n, so that's just root n. So ON is bounded and therefore compact. So yeah, this space of orthogonal matrices, that's a compact Hausdorff space. But so let's also consider SL2 R. So remember, that's the set of A and M2R is det A is 1. So this contains T0, 0, 1 over T. That holds for every positive T, say. So it's therefore unbounded. Because I can take T to be as large as I like, and therefore it's not compact. It is closed because the determinant's a continuous map, so this is det inverse of 1, so that's certainly a closed subset of M. So this is SL2R. Okay, so this is a closed subspace of M2R, but it's not bounded and therefore it's not compact. So that'll do as an introduction to the basic ideas and examples of compactness.